It's a pleasure to be a part of Innovation Martian. Thank you for hosting us today. I promise we'll switch the cameras off in a few minutes just to introduce myself, Francisco de Carvalho. Then we have Stefan Draskoci and Richard Mackenzie, who will cover the business value and the technical options for OpenRAN. For me, it's really just to give a short introduction of my company, Reply, specifically Networks Reply. We're a systems integration company. We specialize in consulting, digital services, anything from requirements captures and business analysis all the way through to the implementation of minimum viable products, proofs of concept, and full rollout. So we have developers, we have project managers, we have designers, we have people that know how to integrate systems. Reply itself is founded in 1996. It has an Italian footprint and ownership with Mario Rizzanti, the chairman, and his daughter Tatiana and Filippo help him to run the business as CEO and CTO. And we're organized into a network of companies. So we cover all of the domains that you care to think about in the digital economy, right through from autonomous vehicles and through to ourselves in telecoms and media. In telecoms and media, we're around a fifth, getting close to 250 million now of the overall revenue for the company. That stands at just under 1.5 million last year. We expect that to be higher at the end of 2022, but we're still calculating the numbers. And as you can see, we cover the globe. The main offices being in Italy, Germany, and the UK in third, but we cover systems, services, customers all the way from Alaska right through to New Zealand. The way we organize in telecoms and media networks of companies is that there's a number of companies in different countries. As I said, we're a global network covering security and network design themselves. So we have companies that do the design and solutions such as Net. We have companies that do the support and the rollout. We have security expertise in Spike. And we also have a Communication Valley company that is kind of an investor, focuses on IoT, but is also looking for talent across the world that may become part of the Reply family. It's very easy in Reply to create new companies. So we have a system, a business case proposition. We have the ability to reuse all of the IT systems. So when a new market opens up and a new business case is produced, such as the Net Reply company in the USA, to actually spin up a new company in the country and the vicinity of the customers of interest, it's an easy process for us to do. Another company that we spun out in 2022 is Next Reply. Next Reply focused on disaggregation. We can go into more details of those capabilities within Reply, but just wanted to give you a flavor of what the company does, how we scale from very small startup mentality and able to take decisions quickly, right through to being able to bring all of these together to deliver large projects. I'm going to hand over now to my colleague, Stefan, and Richard. Richard is going to take control and you'll take us through the rest of the presentation. Thank you for your time.
Cheers, Fran. Yeah, so I'm Richard and I work for BT. And before we go into a lot of the detail that Stefan's going to provide on how they've implemented an OpenRAN network, I thought first we'd just define what an OpenRAN network is, because OpenRAN itself is a very often used term, but it's a very ambiguous term. So what we can see on this first slide is a before and after. So at the top of the slide, we've got the traditional approach where all of the radio equipment is in one location, and that's at the cell site. So that's what we see at the top left. And that all connects to the core network, which is in the top right, and the core network will be highly centralized. Now, if we go to the bottom half of the slide, this is the new OpenRAN architecture. And as you can see, there are more components. And this gives us the flexibility to build a network that can satisfy the user requirements we have for the services we're trying to provide. And what we see here, all these coloured boxes, these are all part of the radio access networks. So in the traditional architecture, this was all at the cell site, but in the OpenRAN architecture, these components can be distributed in different locations. So we still have the RU, the radio unit at the cell site, the distributed unit, and then which is the DU, and the centralized unit, which is the CU. And the DU and the CU can be located at the far edge. Almost the most extreme version is at the cell site still, but we can also centralize them as well, so that the most extreme centralization is if we put them where the core network is. But we can place them in different locations, and that gives us different benefits depending on the service we want. For example, if we want a low latency service, we push everything to the edge. If we want something that's highly cost efficient and secure, we might decide we want to push things nearer to the core. And there's also sort of different ways of coordinating. So we could have multiple radio units connected to a single DU. We can have multiple DUs connected to a single CU. So we get additional coordination between neighboring cell sites via this disaggregated architecture. The other key aspect of OpenRAN is virtualization. So that's implementing the radio functionality in software. So the obvious advantage there is the flexibility. You can change the software very quickly without having to change the hardware. And that leads on to one of the other key characteristics of OpenRAN, which is the multi-vendor aspect. So you'll see on that diagram I've used a lot of colors, and that's just to emphasize the fact that all of these components could come from a different supplier. And that includes, so in the example of the DU, you see the software is a different color from the box below. So the software and the hardware can actually come from different suppliers. So we've got a disaggregated, virtualized, multi-vendor solution. That sounds like a nightmare to control and manage. And that's why the final part of the OpenRAN ecosystem that makes all of this work is that additional box, that dark blue one that's called the RAN Intelligent Controller, or the RIC. So this is the brain of the OpenRAN network. This allows us to automate the network. It allows us to optimize the network. Within every network, there's different sets of requirements, and we have different users that have different requirements. And within the RIC, we can have different features which provide all of the necessary optimizations for the services that we want to provide. So in this diagram, you'll see it's called XApps. So each feature could be called an XApp, and we've used a different color to emphasize again that they could come from different suppliers. So there could be a specialist in one particular type of service that can provide one of the XApps we need, but we don't need to rely on that one supplier for our full suite of XApps. And what's really exciting from an operator perspective, we know our customers as well as anybody, and sometimes the best people to write that XApp might be ourselves. So there's an opportunity there that we don't just have a large ecosystem of XApp suppliers. We can also be XApp suppliers ourselves. I've drawn a simplified diagram here, and you're going to see with Stefan that it can get more complicated, but the RIC does become disaggregated itself into a near real-time and non-real-time components. So XApps reflect the features that do near real-time, and RApps are the equivalent for non-real-time. So the difference is anything that works within a 1 second control loop or above a 1 second control loop. So how are we making this OpenRAN ecosystem a reality? Well, we're working with many industry groups, and in particular the Telecom Infra Project, who are looking to define and build open disaggregated networks. And within TIP, there is the OpenRAN project, and I'm co-chairing a subgroup called the RAN Intelligence and Automation Group. And what we're working on is essentially commercializing the RIC and focusing on the use cases that are the real enablers for us to get the OpenRAN architecture deployed in the soonest time possible, but also maximize the benefit of the RIC. So what we see on this slide, we've now got 17 prioritized use cases. We started with 10, now we're up to 17. And if you're familiar with RAN features, you'll probably recognize a few of these. Some of them are very common, in particular the ones that are categorized as SON features. So SON is self-organizing networks. So these are basic automation features. I say basic, these are already established automation features, and we're just implementing those existing features as XApps or RApps. But there are a number of other features that we've included. One in particular I'd like to draw attention to is massive MIMO. So that's not something that we need in the short term, but there's a huge gain if we can optimize massive MIMO. This is the use of multiple antennas at base stations and at handsets to enable much higher capacity networks. And if we can optimize massive MIMO, we can get huge data rates for all of our users, or more reliable connections, or better service for people that are in a far away from the cell site, or anyone that's in a very dense cluster of users. Massive MIMO can provide benefits in a number of scenarios, but it's very complicated optimization, and so that's a big prize that we're targeting. So we're trying to address it now, but we're expecting the rewards in the years to come. And this is an innovation marsham session, so I don't really need to introduce BT Labs. I'm sure you're all familiar, but this is where we have our first OpenRAN testbed. So next time you're at Adastral, you can have a look around and see if you can spot the equipment. So this is the Orion building, and in the foreground you'll see there's a lamppost with a cabinet, and at the top of that lamppost you'll see there's one of our OpenRAN radio units. And at the bottom of the lamppost you'll see this cabinet, and this is one of the locations where we can run any edge compute. So this is a suitable location for a DU. And then each of these lampposts is fibered back to our data center, and that's where we run any of the centralized components. So that's typically the CU, the RIC, and the mobile core. So this is what you'll see today if you go around Adastral Park, and there's 6 of these lampposts scattered around, so there's a challenge, see if you can find them all. What we're currently doing is running an activity with Acceleran and Viavi, and it's focused on one of those use cases, which is to try and understand where the user demand is within the cluster. This activity is pretty much finished now, and so we're now moving on to a new project, which is ARRI 5G, and this is part of our TIP activities and is with a number of UK partners. We're focusing on several of those prioritized use cases that we saw on the previous slides, and we have XApps coming from 3 different suppliers. So we've got Acceleran, Amdocs, and Viavi providing different XApps for different capabilities, and we're going to be demonstrating them on the 5G OpenRAN network at Adastral Park. And so you'll see us installing the new radio units with cherry pickers around the lampposts in the next few weeks. So if you do see us there and you're interested, feel free to come over and ask questions. And I'll now hand you on to Stefan, who's going to go through some of the details of how he's implemented a RIC.
Thank you very much, Richard. Hi all. As Richard said, I will now give you an insight into the more practical ways in which ORAN can help automate and optimize the radio access network. And I'll start off with a brief use case, an example in which you have a firefighting effort that is surrounded by network cells. Here we have a simplified view where the actual firefighting efforts might be quite a dynamic, let's say, engagement in which you would have added contextual awareness of the specific needs of each of the individual firefighters, as well as, let's say, for example, the vehicles or even drones or UAVs, which are being used to actually spectate and guide the firefighting effort according to the specific needs. That is to say, where the fire is most prominent, which, let's say, aspect is closest to endangering the lives of others. And according to that, we can also derive in context-specific information, which can aid the firefighting effort when it comes to, for example, mobile connectivity. So in this case, we have a few firefighters as well as a drone who have specific needs for their connectivity to the firefighting effort. For example, the drone has a need for high throughput and low latency, and the firefighters themselves, for example, are carrying dash cams, or rather body cams, which are filming their own individual efforts, which are being passed back to the coordination center to aid the overall use case. In this case, we would benefit if there was a centralized means of obtaining network data from the specific users and channeling it into an application, a custom application such as the XApp or the RApp, which would then be able to produce, to analyze that data, to produce a meaningful reconfiguration and reallocation of network resources and apply that in the network such that the firefighters actually obtain the necessary resources in order to support their specific individual needs. And these processes can be achieved through multiple practical, let's say, means and exchanges of information. For example, we have the E2 setup request in the beginning, which is fundamentally the RAN, or rather the whole RAN enabled node latching onto the near real-time RIC and exchanging the information pertaining to what specific, for example, KPIs and capabilities is it capable of sending back to the RIC. The next step is, for example, the A1 policy delivery, in this case via the A1 interface, which sits between the non and near real-time RICs. The non-real-time RIC and the associated RApps can be used to provide policy-based guidance to the near real-time RIC and the associated XApps. So through the A1 policy delivery, for example, the operator can guide the XApp to specific performance needs of individual UEs, as well as, for example, specific KPIs that are to be collected from the associated nodes. This will be followed by the XApp using the guidance to produce a RIC subscription request, which would be sent out to the RAN nodes via the E2 interface. And that would fundamentally set up a subscription for a particular set of, for example, KPIs, which would be reported either with a specific reporting period or based on an event trigger. That is to say, for example, if the resource allocation in this specific node exceeds a certain threshold, then a report is generated and sent via the E2 interface back to the RIC. From there, the XApp can analyze the reported data and produce a necessary reconfiguration. These reports are sent via RIC indication messages. So they are packaged into the RIC indication message that is well defined within the E2 interface, and they are sent via the E2 interface back to the XApp, where they are decoded and analyzed. And then lastly, once the efforts are finished in that specific case, for example, or rather the subscription for that specific KPI is no longer necessary, the XApp can provision a RIC subscription delete request, which would then basically deallocate that subscription from the E2 node. So this gives a relative end-to-end view of the life cycle of the data exchanges happening between the RAN node and the near real-time RIC, and the near real-time RIC and the XApp. And here we have an example of the A1 policy-based guidance. So what you would do is you would define a schema, a JSON schema, that would define the type of payload that you are intending to carry over the A1 interface. And that actual payload would be use case specific. It would have its own policy type, as it's called. And that would be provisioned via the A1 interface from the non-real-time RIC down to the near real-time RIC. From there, once you've registered the specific schema, the actual A1 policy type, you would then provision specific policy instances of that policy type, which would carry, in this case, specific data that is to be analyzed and ingested by the XApp. And then based on that guidance, the XApp is to perform a downstream operation. In this case, you would, for example, send a policy-based guidance, which would instruct the XApp to produce a RIC subscription request towards the E2 node. In this case, we specified a gnode B name, the granularity, that is to say, how often is a report produced by the the E2 node, a reporting period implying how often are the reports being reported back to the RIC. In this case, they're both 20 seconds, so there is one report every reporting period, but the granularity could be, for example, 5,000 milliseconds, which would produce 4 reports every 20 seconds, obviously. You would provision that to 2 specific cells within that gnode B, specifying a RAN function, which is the definition of an E2 service model. That is to say, which specific service-oriented capabilities are offered by that RAN node. And then lastly, the actual KPI that you're trying to report. And once that report is being generated, the report would be sent as a RIC indication message back to the near real-time RIC, and it would be forwarded to the specific XApp which sent out that subscription for that KPI. The payload would be decoded, and it will be then visualized in the dashboard, as well as the XApp itself would be able to store it on the onboard database and over time process it in order to extract useful insights and reconfigurations, which would then be reapplied via the E2 interface back into the RAN node. And here we have a slightly more in-depth, let's say, view into what a typical HORAN architecture would look like. This view is specifically targeting the open source, let's say, space. So you would have the ORAN Alliance-derived near and non-real-time RICs on the right-hand side. You can see the associated interfaces between them, the A1, the E2, for example, the O1. And then you will have on the left-hand side a host of open source virtualized instantiations of the 4G and 5G radio access networks, which, or rather whose instances, the gnode Bs, whether they are separated into CUs and DUs, or if they are just all-in-one, they would be connected via the E2 interface to the E2 termination blocks within the near real-time RIC. And fundamentally, that is via which the whole exchange of information via the E2 interface occurs via this HTTP connection. And then lastly, you would have, again, in the black boxes, the XApps and the RApps that you are deploying on top of the near and non-real-time RIC platforms. And these apps would use the microservices-based nature of the deployment that is in Kubernetes to interact with all of the platform components to achieve specific functionalities. So for example, in the near real-time RIC, you have the subscription manager to which the XApp would talk in order to establish the subscription requests and the subscription delete requests. You have, for example, the E2 termination that is used to decode and encode the specific payloads according to the E2 AP schema. You have the E2 manager that is managing the whole the array of currently connected E2 nodes, and so on and so forth. And if you are interested in how you can benefit from the ORAN ecosystem, how your operations could actually thrive from having the added visibility of the behavior of the network, as well as the ability to analyze that behavior and in the near and non-real-time segments, and then reapply configurations to achieve a desired outcome, please reach out to us.